Here's another example where you're being asked the same thing. I won't work this one out for you. I'll give you a quick little hint to make the calculation a little easier. You might think that this would require product rule, and you could totally do the derivative of this using product rule. But a nice little tip is that x to the 2/3 is the same as x squared raised to the 1/3, which means I'm taking something of the form a to the 1/3 and multiplying it with something of the form b to the 1/3. This exponent rule that I'm showing you will help you with the calculation. In other words, we're going to have x squared times the quantity 6 minus x, all raised to the 1/3 power, is another way to write this function. If you multiply stuff out, you then get 6x squared minus x cubed, all raised to the 1/3. And you can take the derivative of this much more easily, I think. So go ahead, try this problem, and we will move on. Let's look at a different type of problem where we're not given the formula for the function, but we have to try to figure out how to sketch the graph based on the given clues. We're given that f of 0 is 0, f of 2 is 3, f of 4 is 6. These are all points we can actually plot. We're given that f prime of 0 and f prime of 4 are both 0, which means we have horizontal tangent lines there. We saw the three different possibilities that could look like. It could either look like this, or like this, or like that. F prime of x is positive between 0 and 4, and it's negative to the left of 0 and to the right of 4. Second derivative is positive, that means concave up to the left of 2, concave down to the right of 2. Let's take this and try to put it together. We have the point 0, 0, the point 2, 3, and the point 4, 6. I'm going to try to make this graph easier to read, and I'll make this 1, 2, 3, 4, and then 1, 2, 3, 4, 5, and then a y value of 6 would be about there. So we have the point 0, 0, 2, 3, and 4, 6. All right. We have that the derivative at 0 and the derivative at 4 are both 0. So there's a few different ways those could look. The function's increasing between 0 and 4. So the function is all increasing between 0 and 4. It's not necessarily in the shape of a line. We have to remember concavity is involved here. And the function is decreasing before 0 and after 4. Concavity, let's put that together with increase versus decrease. I'm going to label 0, 2, and 4 on this number line, even though the 2 comes from concavity. And then I have my concavity number line. I'm going to label 0, 2, and 4 there. So the concavity is to the left of 2 we have concave up, and to the right of 2, we have concave down. What about increase, decrease? We have the functions decreasing before 0 and after 4. So the function's decreasing before 0 and after 4, and it's increasing between 0 and 4. So I'm going to put 2 plus signs here. And in fact, I should put multiple plus and minus signs in the appropriate place. Again, to the left of 2, we're concave up, and to the right, we're concave down. We have 4 different possibilities here. So what does it look like when a function is decreasing and concave up? That's going to look something like this. What about increasing and concave up? It's going to look something like that. Increasing and concave down, well, it's increasing, but it's spilling water. And then decreasing and concave down, that will look something like that. These 4 pieces down here are exactly what we need to put together to give us an idea of what the curve will look like. So we are doing something like that. That's that piece. And next I'm gonna show this piece. It's gonna come back up till we get to 2. And then between 2 and 4, we're gonna have this type of piece. Increasing, but concave down. Notice what happened here is an inflection point. And then after 4, we are decreasing and concave down, which means the function is going to look something like that. We're going to learn pretty soon a more precise way to make a graph, but everything we're doing here is essentially the idea. And just to summarize some of the points we've been talking about, f is differentiable on an interval. That's the formal way of saying that f is smooth. When we talk about smooth, we talk about differentiable. No points, no skips, nothing like that. First derivative positive means the function is increasing. First derivative negative, function is decreasing. If f prime, the first derivative, changes from positive to negative, that's a local max. If it changes from negative to positive, decreasing and then increasing, that's a local minimum. Second derivative test says that if f prime is 0 and the second derivative is negative, notice this is concave down, then f has a local maximum. If f prime is 0, in other words, horizontal tangent line again, and we're concave up, that's a local minimum. Concave up is first derivative positive. Notice that if the rain falls on either of these, it will collect. But on this, the rain will splash off, and that's concave down. If second derivative changes sign, the point at which that happens, we call that an inflection point. And these are the basics of becoming a graphing calculator, which is one of the main goals of this course.